Hi. In this section, we're going to discuss two fundamental ways that we can work with both matrices and vectors. That is addition and scalar multiplication. Really, all of our work with the three fundamental objects of linear algebra, scalars, vectors, and matrices, would be very limited if we were not also able to define some operations that we can use with them. And there are three fundamental operations that we can sort of define that we'll be using to work with the three fundamental objects. These are addition, scalar multiplication, and matrix-matrix or matrix-vector or vector-vector multiplication, which are all sort of one class. With addition, we can take any two objects of the same size and type and add them together. The way we do this is we simply add the corresponding elements. We can take any object, a vector, a matrix, or another scalar, and multiply that by a scalar. We can think of it as meaning very much the same thing as multiplication of scalars does. The idea of multiplication really means to add an object to itself a certain number of times. Operationally, we perform scalar multiplication simply by taking every element in the object and multiplying it by the same scalar number. Addition and scalar multiplication are quite straightforward. Matrix, vector, vector multiplication is a little bit more tricky. We can define multiplication of vectors with vectors, matrices with matrices, but only according to specific rules that we will outline in a subsequent video. We're going to focus for the time being on addition and scalar multiplication. Addition of scalars is something that we all know how to do very easily. It's one of the first things that you learn to do in terms of math. We extend the idea of addition to vectors and matrices in a really straightforward way. All we need to do is add the corresponding elements. Right? What do we mean by that? If we say that x plus y equals z, it means that every element of z, every zi, is the sum of the corresponding elements of x and y. Right? The vector 0, 1, 2 added to the vector negative 1, 5, 2 is the vector 1 minus 1, or 0, 0 plus 5, or 5, and 2 plus 2, or 4. We just work with corresponding elements. Adding matrices has exactly the same rule. To add the matrix 3, negative 2, 2, 1, and the matrix negative 2, negative 2, 4, 7, we work with corresponding elements. 3 minus 2. 3 minus 2 is 1 for the 1, 1 element of the sum. Negative 2 plus negative 2 is negative 4 for the 1, 2 element. In the second row, we have 2 plus 4 for the first column, or 6, and 1 plus 7, or 8, for the second row, second column. This definition, the fact that what we need to do is add the corresponding elements, leads to two important rules. Objects of different types can't be added. We can't add a scalar to a matrix. They're not the same size. They don't have corresponding elements. We can't add a vector to a matrix. They're not the same size. And even if they are the same type, we can't add them if they are not the same size. A vector of 2 elements cannot be added to a vector of 3 elements. A 2 by 4 matrix cannot be added to a 3 by 3 matrix. Even if they have the same total number of elements, so let's say a 3 by 2 matrix and a 2 by 3 matrix, they're not the same size, they don't have the same number of rows and columns, they can't be added. We wouldn't be able to add them using these rules, because if we tried to, there would be some elements that didn't correspond to one another, that didn't have the same row or in the same column. So this is the rule for how we perform addition of matrices and vectors. This is something that most students, again, tend to find fairly straightforward. Scalar multiplication is also pretty straightforward. Multiplication of scalars is really kind of the second main operation you learn in grade school after addition. It can be related to addition through this idea of adding a value to itself a certain number of times. What is 3 times 2 is the same as 2 plus 2 plus 2, 3 times. That definition, we have to sort of use a little bit of license in extending that to non-integer values, but the same idea sort of holds true basically. We can extend this idea to vectors and scalars in exactly the same way. If we can add matrices and vectors, then we can think about adding a vector to itself a certain number of times, or adding a matrix to itself a certain number of times. This idea of scalar multiplication is executed in a very, very simple way. All we need to do is multiply every element in the matrix or the vector by the same scalar. This kind of follows from the definition. If we want to add a vector to itself a certain number of times, we would add the corresponding values, and each sort of element we would add to itself that same number of times, multiply by that number. So for vectors, k multiplying by u, if such a product equals v, it means that every element of v is the same scalar multiple of k, by the element ui. So 7 times the vector 1, negative 2, 4 is 7 times 1, 7. 7 times negative 2, negative 14. 7 times 4, 28. Matrices follow exactly the same rule. Multiply every element by the same scalar. Half times the matrix 3, negative 2, 2, 1 is half times 3, or 3 halves. Half times negative 2 for the first row, second column, negative 1. For the second row, first column, half times 2 is 1. For the second row, second column, half times 1 is half. Again, this is something that most people do not find too challenging. Because this is what we do, the result of multiplying a vector by a scalar or a matrix by a scalar is a vector or matrix of exactly the same size. Multiplication by a scalar does not change the size of the object we are working with. Once we have scalar multiplication and addition, we can define the idea of a linear combination. Linear combinations are something that we are going to be revisiting throughout the class. It's one of the core concepts in linear algebra. So I'd like to introduce the idea now. We will be coming back to this again later in the class. A linear combination of some set of vectors or matrices is simply a sum of scalar multiples of the set. So we can take vectors or matrices and multiply them by a scalar, add those results together. The result is a so-called linear combination. Right? Some examples: a times x plus b times y equals z. Z is a linear combination of the vectors x and y. Ax plus by plus cz equals w. W, got a little typo here. W is a linear combination of x, y, and z. For matrices, exactly the same idea. A times A plus B times B plus C times C plus D times D equals M means that M is a linear combination of A, B, C, and D. Why do we call these a linear combination? We'll look at the form that we're using. We're taking a constant times a variable, if you will, a constant times a vector. This is the standard linear form that we talked about with a linear equation. And we're taking sums of only linear terms. We call it a linear combination. In a more sort of abstract, more sort of general definition, we can say that if we take a sum over some set of m vectors and we multiply a constant by each of those vectors through scalar multiplication and add all of those terms up, the result is a linear combination of the set. We can apply the same rule to vectors or to matrices and have the same result. Because of how the rules of matrix addition works, vector addition works, and how scalar multiplication works, we can only take linear combinations of a set of vectors or a set of matrices that are of exactly the same size. It doesn't make sense to take linear combinations of objects that are not of the same type or the same size. All right. Now, that was all defined kind of purely in symbolic math. As we discussed in the previous video, it sometimes can be very helpful to think about things geometrically. So I want to briefly discuss how we can think about addition and scalar multiplication geometrically using spatial vectors. Right? Recall that we can, points in space, especially 2- and 3-dimensional sort of space, are vectors. They're ordered sets, and so we can think of vectors in this sort of view of vectors as being points in space or as directed line segments. And it's the latter that tends to be most useful in understanding these operations. If we think of them this way, we can explain addition and scalar multiplication geometrically. Scalar multiplication by a positive value takes a vector, a spatial vector, and changes its length without changing the direction in which it points. Scalar multiplication by a negative value completely reverses the direction that the spatial vector points and if it's not multiplication by -1, also changes the length. Vector addition follows a so-called parallelogram rule that we will sort of discuss in a moment, doing sort of so-called head-to-tail addition. Again, this will be more clear when we show the figure of this. And vector subtraction is the same as adding a scalar multiple of -1. It can also be thought of as directly connecting the points, or doing sort of head-to-head connection of vectors. All right, so that was just a bunch of words. Let's sort of put some pictures associating this. Scalar multiplication by a positive value changes the length of the vector. Imagine that we start with a vector u, represented by the point 1, 3, x equals 1, y equals 3, the directed line segment that goes from 0 to that point. If we multiply that by 3, 3u is the point 3, 9. Multiply each element by the same scalar. And that point, x equals 3, y equals 9, points in exactly the same direction. The directed line segment maps perfectly onto this, but it's 3 times longer. Right? And any scalar multiple by a positive number would lie on this sort of same sort of segment here. If we multiply by a negative number, say for example, -1/2, again the rule is that we multiply both elements by the same scalar. So -1 times -1/2 is 0.5. 3 times -1/2 is -1.5. That's this point here. It lies on the same line. If I sort of drew a line along this vector u, but extending infinitely, that's the little black line here. We see the negative multiple also lies in that point, but it's opposite from the origin. And it's also, because we multiplied by a number less than 1 in absolute value, is shorter than the original vector, half the length in this particular case. So scalar multiplication really simply corresponds to a scaling, this is where the term scalar comes from, of the vector, of the directed line segment representation of that vector. What about addition? Well, vector addition, imagine that we start with a vector u, the same one, u1, 3, and another vector v, -2 and 1. When we add them together, we add the corresponding terms. So 1 plus -2 is -1. 3 plus 1 is 4. The sum of these is the point 1, 4, which is here. This vector lies at the corner of a parallelogram formed by using u and v as two sides and then completing the parallelogram. So from the end of v, we extend a line perfectly parallel to and exactly the same length of u. From the end of u, we extend a line perfectly parallel to v. And we end up with that corner point is the same. We can think about this addition as kind of first walking along the vector u, and then starting from the point u rather than starting at the origin, following the vector v until we get to this point. Right? U plus v leads us to this point. The order of addition doesn't matter. If instead we first of all walked along v and then added u, we would end up in the same point. This gives us a sort of a geometric interpretation of what it means to add two vectors. we'll sometimes see subtraction of vectors. It's worth thinking a little bit about what the geometry of vector subtraction is. If I have a vector u, and again this same vector v, what would u minus v be? U minus v is u plus negative v. 1 minus negative 2, or 1 plus 2, is 3 for the first element. 3 minus 1, or 2 for the second element. That puts us over here. U minus v is the point over here. One way we can get to that point is by taking u and adding the line negative v. Right? Would take us to this point. But another way of getting that same sort of line is to directly connect the heads of u and v. And if we go from v to this point u, we get the value uv. You can sort of think about this in a little bit more sort of abstract terms. If we first of all walk along v, and then we walk along u minus v, what are we doing? We're adding u and subtracting v. Well, we already added v, so if we now add u and subtract v, we ought to get back to u, which is exactly what happens. Right? The difference uv is sort of the connection from v to u. V minus u has the same interpretation, just in the different direction. So v minus u also is the vector that connects the points u and v, but starts at u moving to v. We move along u and then add v and subtract u. We get us back to v. Thinking about this in terms of a parallelogram, if we take v and we then add to it negative u, we get to this point here, v minus u. V minus u is negative 2 minus 1, negative 3. 1 minus 3 is negative 2. This representation of vector subtraction is something that you might see a little bit less often, but it does have this geometric representation. The representation of scalar multiplication and vector addition is something that really is important to internalize. It really can help in understanding what we're doing when we work with these two operations with vectors. All right, so I'm going to sort of stop this video here. There will be an accompanying video where we go through some worked problems involving addition and scalar multiplication of vectors and matrices, and a follow-up lecture where we're going to dig into the multiplication of matrices with other matrices and vectors. Thank you and goodbye.